Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. I'm Philip Emeagwali. In 1989, I was in the news for inventing how to solve the most compute-intensive mathematical problems that arise as the partial differential equations of calculus. I was in the news for inventing how to solve the largest system of equations that occur in computational linear algebra that approximated the system of partial differential equations that governs planetary-scaled fluid dynamics motions. The poster boy of such grand challenge problems is the supercomputer simulations of long-term global warming. After July 4, 1989, I was in the news for inventing how to solve the companion initial boundary value problems and how to solve them at the fastest speeds and solve them across a new internet. I visualized that new internet as my new global network of 64 binary thousand processors. I visualized those processors as coupled, identical, equal distances apart, and sharing nothing. That new internet is a supercomputer in reality. That supercomputer is an instrument of mathematics and physics. The fastest supercomputer is the flagship computer of the world. My contributions to mathematics were these. I discovered how to solve nonlinear partial differential equations and how to solve them across a new internet. That's a new global network of off-the-shelf processors that were identical and coupled and that shared nothing, but were in dialogue with each other. A complex system of nonlinear partial differential equations, or PDEs, is impossible to solve exactly and impossible to solve on the blackboard. However, the most important system of nonlinear partial differential equations can be solved approximately on the computer and solved with the most accuracy across a new internet. That's a new global network of up to 1 billion off-the-shelf processors. In calculus textbooks, some linear partial differential equations can be solved exactly and solved by using the technique called Fourier series expansion and using it to solve an initial boundary value problem governed by the heat conduction equation in one dimension. The heat equation is used to model the diffusion of particles. The heat equation is used to describe the macroscopic behavior of microscopic particles in Brownian motion or the random movement of fluid particles. That initial boundary value problem has Dirac-Clay or first-type boundary conditions that specify the solution along the boundary of domain of the problem. In the 1980s, I used the exact solutions of linear partial differential equations to validate my parallel processed codes. Partial differential equations go by different names that depend on the assumptions and settings used to derive each. The coupled system of 9 Philip Emeagwali partial differential equations is the mathematical language that I invented and used to describe the flows of crude oil, injected water, and natural gas flowing up to 7.7 miles or 12.4 kilometers below the surface of an oil field. That's almost twice the size of Anambra, my state of origin in Nigeria. The 9 Philip Emeagwali equations were based on my corrected assumption that inertial forces exist within all producing oil fields. Philip Emeagwali equations are the most complicated equations in physics. My contributions to mathematics were these. I mathematically encoded the temporal and the convective inertial forces that exist within all producing oil fields. I encoded both physical forces into 36 partial derivative terms, and I added those mathematical terms to the existing 45 partial derivative terms described in computational physics textbooks on subsurface petroleum reservoir simulation. The grand challenge, initial boundary value problem of mathematics, is so named because it requires tremendous supercomputer power to solve it with an acceptable accuracy. On my eureka moment, which occurred at 15 minutes after 8 o'clock in the morning of the 4th of July 1989, I discovered how to parallel process 30,000 years of time to solution of a grand challenge problem to 1 day of time to solution across an ensemble of 10.65 million off-the-shelf processors. Although parallel processing entered the realm of science fiction and did so on February 1, 1922, it wasn't until my discovery, which occurred on July 4, 1989, that a full understanding of the vital technology that underpins the world's fastest computer was attained. In 1922, weather forecasting across 64,000 human computers was written as a science fiction story. My contributions to physics were these. On July 4, 1989, I discovered how to upgrade the science fiction of forecasting the weather across 64,000 human computers to the non-fiction of forecasting the weather across 64 binary thousand processors or across as many electronic computers. I contributed to physics by discovering how the extreme scaled climate model is parallel processed across a new internet, that's a new global network of 65,536 processors, and how global climate models can be executed by chopping up the model of the Earth's atmosphere and oceans into 65,536 smaller climate models that are mapped with a one model to one processor correspondence and mapped onto as many processors. The societal importance of my contribution to science is this. Parallel processed climate models are tools used by decision makers to help ensure the Earth is safe for humans and for all animals. In 1989, it made the news when I discovered how to solve the most compute-intensive problems in mathematics and science. I was cover stories because I discovered how to solve the world's biggest problems in mathematics, physics, and computer science, and solve them at the fastest recorded computer speeds. I invented how to solve the most compute-intensive mathematical problems called extreme-scale computational fluid dynamics, and solve them across a new internet That internet was a new global network of up to 1 billion identical and coupled processors. Each processor operated its operating system. Each processor was self-contained and had its dedicated memory and shared nothing. I was in the news because I invented a new internet, that's a new global network of millions or billions of processors. I invented how to parallel process or how to execute a billion set of computer instructions and how to execute them at once or how to execute them in parallel and across up to a billion processors. For the 25-year-old mathematician, the expression partial differential equations of mathematical physics conjectures up images of the parabolic heat equation, the hyperbolic wave equation, and the elliptic Laplace equation described in his mathematics textbooks. The real-world problems that arise in mathematical physics occur while handcasting the weather up to 7.7 miles or 12.4 kilometers below the surface of the earth. The world's biggest problems include the handcasting of the quote-unquote weather deep inside the Niger Delta oil fields of southern Nigeria. Another large-scale computational fluid dynamics problem that's equally compute-intensive is to forecast the long-term weather above the surface of the earth, or to simulate the spread of a once-in-a-century global pandemic's contagious viruses across the 2.5 billion passengers a year that ride in Russia's Moscow metro. These real-world initial boundary value problems that are governed by partial differential equations of mathematical physics can't be analytically solved on the blackboard, or solved with pencil and paper, or solved with a computer that's powered by one processor. The world's most compute-intensive mathematical problems must be solved only across an ensemble of millions of processors that were identical and that shared nothing. As a research computational mathematician who came of age in the 1970s in Corvallis, Oregon, and 80s in College Park, Maryland, Washington, District of Columbia, and Los Alamos, New Mexico, my mathematical grand challenge was to invent the correct system of partial differential equations called the 9 Philip Emeagwali equations that governs the flows of crude oil, natural gas, and injected water that are flowing across any of the world's 65,000 producing oil fields, including Nigeria's 159 producing oil fields. My system of partial differential equations were not published in any calculus textbook of the 1980s. As their sole inventor, I was the first person to formulate and discretize them and consequently derive their companion system of partial difference equations of large-scale computational linear algebra. I invented both my systems of differential and difference equations from my correct formulation of the second law of motion of physics. I discovered how to chop up the most compute-intensive problems as the 64 binary 1000 high-resolution computational physics codes that I must parallel process and that I must map in a one code to one processor corresponding fashion, and that I must evenly distribute onto as many off-the-shelf processors that outline and define my new internet. My new internet was a virtual supercomputer in reality. That one code to one processor mapping was the grand challenge of extreme scaled computational mathematics, such as global climate modeling, to foresee otherwise unforeseeable global warming. What are the contributions of Philip Emeagwali to mathematics? Often, scientific recognitions lack a sense of proportion and context. My mathematical discovery of 36 partial derivative terms that must be used to accurately pinpoint the miles deep locations of crude oil and natural gas deposits is abstract, and it's not as important as my scientific discovery that the fastest computer can be built with the slowest processors. The latter contribution was a scientific breakthrough and subject of newspaper articles, and became the vital technology that underpins every supercomputer. Inventing my new 36 partial derivative terms requires very high-level, dense mathematics to explain all the mathematical steps that I took over a 15-year period. The simplified explanation of my mathematical invention, that is my contribution to mathematical knowledge, is that both the temporal and the convective inertial forces that exist in the actual problem must also exist on the blackboard and motherboard, and must be represented by those 36 partial derivative terms. Inventing a new system of partial differential equations of calculus and discretizing those equations into a new system of partial difference equations of large-scale computational linear algebra, and experimentally proving the stability and convergence properties of the companion partial difference algorithms, and coding those algorithms across a monumental ensemble of off-the-shelf coupled processors that shared nothing, was a notable problem that was defined at the crossroad where new physics, new mathematics, and the world's fastest computing intersected. In 1989, I was in the news for solving that grand challenge problem, and for solving it alone. The parallel supercomputer that occupies the space of a soccer field is a supersized mathematical instrument that put the partial differential equation back whence it came from. It's not enough to lecture on the mathematical foundation of the fastest supercomputers, even though that intellectual feat requires mastery of physics, mathematics, and computer science. It took me 20 years to arrive at the frontiers of knowledge of physics, mathematics, and supercomputing. I was in the news because I discovered how to solve the most compute-intensive mathematical problems, such as initial boundary value problems governed by a system of partial differential equations. I discovered how to solve partial differential equations across an ensemble of up to 1 billion processors. Such equations contextualized and encoded some of the most important laws in physics. Such equations capture in a few succinct terms some of the most ubiquitous features of the air and water flowing across the surface of the earth, including the atmosphere and oceans, and the crude oil, injected water, and natural gas flowing across highly anisotropic and heterogeneous producing oil fields that are up to 7.7 miles or 12.4 kilometers below the surface of the earth. An oil field is about the size of a town. My contributions to supercomputing, as it's executed today, push the boundaries of modern mathematical physics to include fastest computing across up to 1 billion processors. I couldn't have accidentally discovered a more accurately formulated system of partial differential equations and discovered it without knowing what's erroneous with the century-old partial differential equations that were published in textbooks. After 16 years of mathematical research, I became fearless in the face of the partial differential equations arising at the frontier of calculus. After 16 years, I developed the mathematical maturity that was needed to read the physics text subtext encoded into partial differential equations, and needed to understand what their partial derivatives represent. I would introduce new partial derivatives and introduce them into the partial differential equations and where they were missing. After 16 years, I gained the ability to discretize any partial differential equation and to solve it on a computer or solve it across a new internet that's a new global network of coupled processors. I knew partial differential equations, not by memorization, but through understanding them enough to invent new ones. I understood partial differential equations deeply. I could look in the mathematical physics textbook and see which key partial derivatives were missing from the system of partial differential equations that were used by computational physicists and used to simulate the flows of crude oil, natural gas, and injected water that were flowing up to 7.7 miles or 12.4 kilometers deep and flowing across a highly anisotropic and heterogeneous producing oil field that's up to twice the size of the state of Anambra, Nigeria. After 16 years, with foremost American and visiting European mathematicians, I developed the ability to translate verbal statements of the laws of physics and translate them into partial differential equations that arise beyond the frontier of calculus. Likewise, I developed the ability and the intuition that was needed to move back and forth between the laws of physics and the partial differential equations that arise beyond the frontier of calculus. Furthermore, I developed the mathematical maturity needed to identify connections between the weather above the surface of the earth and the weather below the surface of the earth. Not only that, I could spot century-old mathematical errors in textbooks and correct them. I could draw a line between the partial differential equations we know and the ones we don't know. How did I solve the most difficult problem in computational mathematics? I could use my instinct and intuition to solve initial boundary value problems in extreme scale mathematical physics. A calling for solving unsolved problems of mathematics is needed, just like it's impossible for you to set the world record in a 26.2 mile or 42 kilometer marathon race and do so without extensive training in long distance running. It would have been impossible for me to set the world record of the fastest mathematical computations that I executed on the 4th of July 1989 in Los Alamos, New Mexico, USA, and set that record without my 16-year-long training as a research computational mathematician in the USA. In 1989, what made the news headlines was that an African-born computational mathematician has discovered how to perform the fastest mathematical computations I did so by changing the way we count, namely my alternative way of counting up to 1 billion things at once instead of the old way of counting only one thing at a time. The old way of counting was used since the era of our prehistoric human ancestors. The paradigm shift from the sequential way of counting to the parallel way of counting is to the mathematics textbook what the continental drift was to the geology textbook. What are the importance of the Philip Emeagwali equations? To contribute new mathematics is to add new knowledge to the existing body of mathematical knowledge. The 9 new partial differential equations that I invented were cover stories of top mathematics publications such as the May 1990 issue of the Siam News, which is the flagship publication for the research mathematician. My partial differential equations are for discovering and recovering otherwise undiscoverable crude oil and natural gas formed up to 541 million years ago and buried up to 7.7 miles or 12.4 kilometers deep. Without the fastest computing across millions of processors that I discovered, the solution of the most compute-intensive initial boundary value problems, such as the simulation of long-term climate change, will be as approximate as a sketch instead of as exact as a photograph. In theory, mathematical predictions based upon the partial differential equations should be as reliable as a hammer. In practice, it's a different story. The world's fastest computer shortens the gap between theory and practice. The Philip Emeagwali equations are correct and accurate, and for those reasons also shorten the gap between theory and practice. What are the contributions of Philip Emeagwali to mathematics? A significant contribution to mathematical knowledge can be made only by a person who has spent 3 or 4 decades training as a research mathematician and as a polymath who has reached the uncharted waters of mathematical and scientific knowledge and went beyond the unexplored territory of human knowledge where new mathematics can be discovered. My journey was to the terra incognita of mathematical knowledge, where I became the first person to figure out how to solve never before solved problems. Beyond the mathematics textbook, such grand challenge problems exist beyond the mathematician's blackboard. Such troublesome problems were formulated for physical domains up to 7.7 miles or 12.4 kilometers beneath the surface of the earth. A grand challenge problem is in contrast to mathematical problems formulated only for the mathematician's textbook and blackboard. It took me 2 decades of full-time training to contribute the knowledge of the world's fastest computing to both mathematics and physics. It took me the first 16 years in the USA following March 24, 1974 to gain the mathematical maturity needed to solve advanced mathematical problems in planetary scaled geophysical fluid dynamics. During those 16 years, I constantly struggled against the most compute-intensive problems that span disciplines from geology to meteorology, from the partial differential equations, beyond the frontier of calculus, to the processor-to-processor emailed codes of computational physics, and from extreme-scale algebra to supercomputing across 1 billion processors that outline a new internet, that's a new global network of coupled processors. I grew as a research mathematician and did so during those 16 years or more of solving increasingly challenging problems that arose at the crossroad where new mathematics, new physics, and the world's fastest computing intersect. My quest for the world's fastest computing started as the world's slowest mathematician. That quest began from the times table that I learned in the first grade at age 5 in January 1960 in Sapele, Nigeria. It grew to the fastest multiplications that I recorded on the 4th of July 1989 in Los Alamos, New Mexico, USA. That technology underpins the fastest parallel processed computations that I invented. It's used to solve real-world mathematical problems, such as making possible your evening weather forecast that's based upon extreme-scaled computational physics that must be executed across an ensemble of up to 10.65 million off-the-shelf processors. 2,300 years ago, King Ptolemy I of Egypt demanded from the father of geometry, Euclid, an easier path for his son to follow and understand geometry. He is a prince, said King Ptolemy. There is no royal road to geometry, Euclid replied. My contributions to mathematics and physics were these. I discovered a royal road to the farthest frontier of calculus. My royal road led to the solution of the most compute-intensive problems in mathematics, physics, and computer science. That grand challenge problem was to find the solution to the discrete approximations of initial boundary value problems beyond the frontiers of calculus, computational physics, and supercomputing, and doing so across a global network of up to 1 billion processors that is an internet. My discovery of the world's fastest computing enabled the supercomputer to become the workhorse of large-scale computational mathematicians and physicists. In supercomputing, 9 out of 10 cycles are consumed by modelers solving grand challenge problems that are governed by systems of partial differential equations and their companion and approximating system of partial difference equations. The partial differential equation of calculus is an equation for some quantity called a dependent variable. That dependent variable depends on some independent variables and involves derivatives of the dependent variable with respect to at least some independent variables. For 4 decades, I researched partial differential equations that govern both the quote-unquote weather up to 7.7 miles or 12.4 kilometers below the surface of the earth, and the weather above the surface of the earth. These are by far the most important partial differential equations in mathematical physics. My contributions to mathematical knowledge that made the news headlines in 1989 were these. I discovered a royal road to the farthest frontier of human knowledge of large-scale computational and mathematical physics. My discovery of the world's fastest computing is my signature contribution to human knowledge. My discovery led to the parallel processed solution of the largest scale problems in computational physics. It led to solving real-world initial boundary value problems and solving them across 64 binary thousand processors that were coupled and shared nothing. My discovery of fastest computing yielded the vital technology that now underpins every supercomputer. For those reasons, my invention was later acknowledged by then US President Bill Clinton, who did so in his White House speech dated August 26, 2000. Likewise, my invention was acknowledged in the news headlines of 1989 and later. Since 1989, my invention has been the subject of school essays on computer pioneers and their contributions to the development of the computer. Since June 1974, a Thursday that I remember because a total solar eclipse occurred and the moon passed between the earth and the sun. And since that rare astronomical event, my quest for the fastest supercomputer on earth hinged on the most consequential issue in computer history. In computing, the biggest question was this: how do mathematicians solve a grand challenge problem at the intersection of mathematics, physics, and computer science? Or how do mathematicians solve the initial boundary value problem of large-scale mathematical and computational physics? And how do mathematicians discretize that difficult problem? And do so by dividing the resulting system of equations of extreme scale algebra into up to a billion smaller systems, and solving those small systems across an ensemble of up to a billion off-the-shelf processors that were identical, coupled, and shared nothing. Each processor operated its operating system and had a one-to-one correspondence with the as many problems. There is no precise set of rules for solving unsolved problems. The best we can do is to keep searching for answers. My quest for the world's fastest computer was both a journey and a destination. My scientific discovery of how to manufacture the fastest computers and do so with standard parts fueled the quest for a new destination, namely the next horizon to answering the most difficult questions in modern computer science. That new horizon is to invent the quantum computer and, most importantly, to use the technology to address the toughest questions in science. That new technological horizon resides within the realm of computer science fiction and is still beyond our understanding. I walked alone because my world's fastest computing that was enabled by the world's slowest processors was ridiculed by the likes of Steve Jobs and dismissed as a noble but distant dream. My discovery of the world's fastest computing was at first theorized and therefore was expected, yet it was an otherworldly new knowledge. The world's fastest computing was my 1989 holiday gift to the US for its Independence Day of the 4th of July, that's Nigeria's equivalent of October 1. A scientist achieves immortality by first discovering something that will be forever remembered. For me, science is more than learning science. My science is a search for something unknown, such as the invention of the world's fastest computer as it's known today and as it's expected to be known tomorrow. Thank you very much. I'm Philip Emeagwali. Thank you. Thank you very much.
Insightful and brilliant
Thank
lecture.
You.